A small pin fixed on a tabletop is viewed from above from a distance of 50 centimeter. By what distance would the pin appear to be raised if it is viewed from the same point through a 15 centimeter thick glass slab held parallel to the table? Refractive index of glass equal to 1.5. Does the answer depend on the location of the slab? Here we can see that a pin is fixed on a tabletop, which is the object O, and a glass slab is placed on the table, and this pin is viewed from the top of the glass slab from 15 centimeter height. Now we know that when an object is at denser medium and the observer is in the rarer medium, the normal shift, which is delta D, is equal to T into 1 minus 1 by mu, where T is the thickness of the slab. So here delta D equal to 15 into 1 minus 1 by 1.5, since the thickness of the slab has been given as 15 centimeter and refractive index of the glass is given 1.5. So we get 5 centimeter. This is the normal shift. So the observer sees the image of this pin at point I, and here IO is the normal shift. Now, normal shift delta D depends only on the thickness of the slab T and the refractive index of the material of the slab, that is mu, for small angle of incidence. It does not depend on the location of the slab. Figure shows a cross section of a light pipe made of glass fiber of refractive index 1.68. The outer covering of the pipe is made of a material of refractive index 1.44. What is the range of the angles of the incident rays with the axis of the pipe for which total reflections inside the pipe take place, as shown in the figure? Since total reflection occurs at Q, let the ray be incident at an angle I at point P, and it suffers a refraction and goes along the path PQ, and at point Q it suffers total inter-ray reflection. So I dot, which is the angle of incidence at point Q, must be greater than equal to the critical angle between the surface of these two media. That is I dot greater than equal to theta c, where theta c is the critical angle. We know that total internal reflection occurs only when angle of incidence at the denser medium is greater than critical angle theta c. So the minimum value of I dot for which total internal reflection takes place is equal to theta c. Now here we find the value of theta c from Snell's law. When the light ray is incident at an angle theta c at point Q, the light ray goes along the surface of the two media. So angle of refraction is 90 degree when angle of incidence is equal to theta c, and applying Snell's law we get 1.68 sine theta c equals to 1.44 sine 90 degree, or after calculating we get theta c is approximately equal to 59 degree. So we get I dot mean equals to theta c equals to 59 degree, that is it is also equal to 59 degree. Now from the figure we can see that I dash plus R is equal to 90 degree. This is a right angle triangle, so we get I dot plus R equals to 90 degree. So when I dot is minimum, R will be maximum. So the value of R maximum equal to 90 degree minus I dot minimum, and we get 31 degree. This is the value, maximum value for R at point P, that is angle of refraction of R at point P. Let I max be the maximum angle of incidence at point P for which total reflection occur at Q. Now if we apply Snell's law at point P, we get sine I max equals to 1.68 sine R max, or after calculating we get I max equals to 60 degree approximately. So the range of the angles of incidence for total reflection inside the fiber is from 0 degree to 60 degree. If the light rays at point P be incident at an angle greater than 60 degree, that at point Q no internal reflection takes place. We can use the formula for maximum angle of incidence, that is I max equals to sine inverse root over mu2 square minus mu1 square. Here mu2 equals to 1.68 and mu1 equals to 1.44, and we get I max equals to 60 degree. What is the answer if there is no outer covering of the pipe? Now let the outer covering of the pipe has been removed. So this pipe now behaves as a slab of material with refractive index mu equals to 1.68. When there is no outer covering of the pipe, critical angle of glass air interface becomes theta c equals to sine inverse 1 by mu, or we get 36.5 degree. Now, if angle of incidence at P is maximum, that is I equals to 90 degree, at point P, angle of incidence for the light ray may vary from 0 degree to 90 degree. Now, we take the case when the angle of incidence is maximum, that is I equals to 90 degree. Then from Snell's law, we get sine 90 degree equals to 1.68 sine r, where we have taken the angle of refraction at point P is r, or which gives r equals to 36.5 degree. In that case, I dot equals to 90 degree minus r. So 90 degree minus 36.5 degree equals to 53.5 degree, which is greater than critical angle theta c. We have already calculated critical angle theta c as 36.5 degree, and we can see that for maximum angle of incidence at point P, the angle of incidence at point Q is greater than critical angle theta c. So total internal reflection takes place. Now, if the angle of incidence at P, I decreases, then R also decreases and I dot increases. So all incident ray will suffer total internal reflection. We have already taken that at point P, the light ray is incident at maximum angle, that is 90 degree. Now, if the angle of incident decreases at P, eventually the angle of refraction at P, that is R, will also decrease. And when R decreases, I dot increases, since we have I dot equals to 90 degree minus R. So when R decreases, I dot increases. If I dot increases, so it will remain greater than critical angle theta c. So total internal reflection will take place. So all incident ray will suffer total internal reflection. That is, at point P, if light ray is incident at angle 0 degree, total internal reflection will occur. And if the light ray is incident at angle 90 degree, then total internal reflection will also occur. The image of a small electric bulb fixed on the wall of a room is to be obtained on the opposite wall 3 meters away by means of a large convex lens. What is the maximum possible focal length of the lens required for the purpose? When there is a fixed distance between object and the screen O and S, and we wish to obtain a sharp image on the screen by placing a convex lens in between object and screen, the minimum focal length required F must have satisfy a condition that F must be less than equal to 4D. Condition for obtaining a sharp image on a screen located at a distance capital D from the object by a lens of focal length f is d square minus 4df greater than equal to 0, or d greater than equal to 4f, or we can say that 4f must be less than equal to capital D. Now for maximum value of f, we must have f equal to d by 4, that is 3 by 4 meter or 0.75 meter. A screen is placed 90 centimeter from an object. The image of the object on the screen is formed by a convex lens at two different locations separated by 20 centimeter. Determine the focal length of the lens. Let the object O and the screen S is separated by a distance 90 centimeter, and when we place a convex lens of focal length f into different positions in between the object and screen, that is at position L1 and L2, in both the cases we get a sharp image on the screen. Let the separation between these two positions be x, which is given as 20 centimeter. For fixed distance capital D between object and screen, if separation between two positions of the lens of focal length f is x, for which a sharp image is formed on the screen, then we have the equation f equal to capital D square minus x square by 4 capital D. Here D is given 90 centimeter and X as 20 centimeter. That is, the separation between the two locations L1 and L2 is given as 20 centimeter. If we put these values, we get F equals to 21.4 centimeter. Determine the effective focal length of the combination of the two lenses in exercise 9.10 if they are placed 8 centimeter apart with their principal axis coincident. Does the answer depend on which side of the combination a beam of parallel light is incident? Is the notion of effective focal length of this system useful at all? In exercise 9.10, two lenses were given, one a convex lens of focal length 30 centimeter and another a concave lens of focal length 20 centimeter. So we take two lenses, one convex lens of focal length 30 centimeter and another concave lens of focal length 20 centimeter, which are separated by a distance of 8 centimeter. Now we have to calculate the effective focal length of this system. Let at first we take that the parallel beam be incident first on the convex lens from left. That is, for convex lens, U1 equal to minus infinity and F1 equals to plus 30 centimeter. So from lens formula, if we put these values, we get V1 equals to plus 30 centimeter. So if the concave lens was absent, the convex lens would have formed an image at a distance 30 centimeter from the lens. So image would have been formed at a distance 30 centimeter to the right of the convex lens, that is at point I1 in the absence of the concave lens. This image I1 behaves as virtual object for concave lens. So for concave lens, object distance U2 equals to plus 22 centimeter and F2 equals to minus 20 centimeter. So from lens formula, if we put these values, we get V2 equals to minus 220 centimeter. So the final image is formed at a distance 220 centimeter to the left of the concave lens. That is, the parallel incident beam appears to diverge from a point 216 centimeter from the center of the two lens system. This can be considered as the effective focal length of this system. We have calculated the effective focal length from a point which is the midpoint of the two lenses, that is from point P. So effective focal length for this combination is 216 centimeter from the center of the two lens system when parallel beam first incident on the convex lens. Now let us take parallel beam be incident first on the concave lens. So for concave lens, object distance is minus infinity and focal length is minus 20 centimeters. So from lens formula, if we put these values, we get V1 equals to minus 20 centimeter. That is, image distance is 20 centimeter. Our virtual image I1 is formed at a distance 20 centimeter to the left of the concave lens. Now this image I1 behaves as the object for the convex lens. So object distance for the convex lens is 20 centimeter plus 8 centimeter. That is 28 centimeter. So for convex lens, object distance is minus 28 centimeter and focal length is plus 30 centimeter. So from lens formula we get V2 equals to minus 420 centimeter. So final image I2 is formed at a distance 420 centimeter to the left of the convex lens. This is the final image, which is at a distance 420 centimeter from the convex lens. That is, the parallel incident beam appears to diverge from a point 416 centimeter from the center of the two lens system. This can be considered as the effective focal length of the system. So here the effective focal length becomes 416 centimeter. Whereas in the first case, the effective focal length was measured as 216 centimeter. So the answer for effective focal length of the combination depends on which sides of the combination a parallel beam of light is incident. So the notion of effective focal length of this system is not useful. If the separation between the two lenses is very small compared to the focal length of the lenses, that is if d much less than f1 and d much less than f2, then effective focal length Fe is given by the equation 1 by Fe equal to 1 by f1 plus 1 by f2 minus d by f1 into f2.